Hello everyone, this is Professor Iris Miano, your professor for Math 32 and Plane Geometry at Santa Monica College, giving you your Week 9, Day 17 lecture video concerning only one section, 6.3, the rectangle, square, and rhombus. So this is where we get to know the rest of our quadrilaterals in some detail. Furthermore, this is the last section of Unit 3. So this will conclude the sections that you will need to study in order to be prepared for Exam 3. Just to be clear, Exam 3 spans all of Chapter 5 and Chapter 6 sections. And this is the last such section in Chapter 6. So here we go. Let's go ahead and start by defining what a rectangle is. And I know we have some preconceived notions, probably, of what a rectangle is, and maybe you have a definition in your mind that's something of the sort of a four-sided figure in which, opposite sides are congruent. And while that is true about a rectangle, technically, for our purposes, the definition of a rectangle is that it's a parallelogram that has a right angle. Yes, you read that right. A parallelogram that has a right angle. Seems like a weird definition, right? So think of a parallelogram. Here is probably what we would visualize as a quintessential parallelogram here, and just kind of straighten it up a little bit. And you only need put a box in one of the interior angles in order to categorize it as, let me go back one, as a rectangle, believe it or not. Now, by corollary, directly after the definition here, we can actually go on to conclude that rectangles have all of their interior angles as right angles as well. And then, of course, there's more to it with the opposite side lengths, and also, but we're not going to get into that detail just yet. So go ahead and, yes, in your there's a space dedicated to this figure on your lecture notes. Go ahead and add right angles all in there if they are not already present. Okay, so then furthermore, what can we conclude about rectangles? Well, it turns out that their diagonals are congruent. So it makes sense. If you recall, there was a theorem in one of the previous sections concerning parallelograms in which the diagonals were comparable according to the opposite angle that they were connected with, and if the opposite angle was the obtuse angle, then it would be the longer diagonal, or if it was opposite the acute angle, then it would be the shorter diagonal. Well, all of the angles in a rectangle are the same. They're all 90 degrees, right? And since they're all equal to each other, then that means that the diagonals that a rectangle would exhibit would have to have equal lengths to them. And so if quadrilateral ABCD is a rectangle, using this corollary, we can therefore conclude that the diagonals AC and BD are therefore congruent to one another. Okay? Very good. Continuing. Let's define what a square is. Again, I'm sure everybody's got preconceived notions of how they define a square based on their previous institutions or, courses that they've taken elsewhere, but for our purposes, a square is a rectangle that has two congruent adjacent sides, like so. So here's a quadrilateral ABCD. Let's say, for the sake of argument, that it's a rectangle, but two of the adjacent sides, I'm going to specify them specifically with this figure as side lengths AD and CD. If they're congruent to each other, then that means that this is a square, okay? AD is congruent to CD. Sorry, I'm getting ahead of myself with my forward clicking, but yes, that'll help us be able to conclude that we're talking about a square, or if a quadrilateral is defined as a squared, this is a conclusion that you can draw. Remember, the information associated with definitions is biconditional, which means you can start with the definition associated with the term that's being defined and then categorize it as that term, or you can, if a item is defined in a certain way using a term, then you can use the definition content in order to draw a conclusion. You can go in both directions is all I'm saying, okay, just as a reminder. Next, we have a corollary associated with squares. So say you have a square A, B, C, D, as pictured here, it turns out you get to conclude that all of the side lengths are congruent to each other. So you can make this string congruency statement and put a single tick mark on all of the outside edges in order to indicate their relationship of being congruent to one another. Okay, great. Moving on. Let's define what a rhombus is. A rhombus is also commonly called a diamond, but the technical term for it is a rhombus. And what is it? It's a parallelogram with two congruent adjacent sides. So think of your some sort of parallelogram. I'm going to fudge it a little bit by giving you a figure that is definitely a rhombus, but you only need to have two congruent adjacent sides. Now I chose the side lengths AD and CD as being the pair of congruent sides, but it could have easily been any other two adjacent sides. So remember, adjacent means that the sides have to share a vertex. In this case, the vertex that's shared is D. Okay? It's a stylistic choice that I'm making here, but yeah, if these two adjacent edges are congruent and otherwise the quadrilateral is defined as a parallelogram, then you can further categorize it as a rhombus or vice versa. If you're given a quadrilateral that's called a rhombus, then you can choose any two edges and say that they are a congruent matched pair by definition. Okay? By corollary, not by definition, we get to conclude that actually all sides of the rhombus are congruent. And this is something that probably a lot of folks identify as part of the definition, but technically it's not. So by corollary, which is kind of a sub-theorem, if you have a rhombus ABCD as pictured here, you get to actually make the string congruency statement that all of the outside edges are congruent to each other. And there you go. And there's the tick mark notation as we've seen previously. That's linked to this string congruency statement. Moving on. Ooh, this is where it gets real fun. Turns out that by corollary, rhombus has diagonals that happen to be perpendicular to one another. And if you recall, perpendicular lines form right angles. And so you can say that any one of these interior angles where the two diagonals are crossing could be categorized as a right angle. And you can state here that, of course, the two diagonals AC and BD are perpendicular to one another using this little upside down T symbol, which we all know by now it means is perpendicular to. Okay? But wait, there's more. Not only are the diagonals of a rhombus or a square perpendicular, but they're also bisectors of one another. So we can move a little bit further with this idea by letting diagonals AC and BD intersect at a named point E, and then not only is there a right angle formed in any of the interiors of the four angles being formed by the crossing of the two diagonals, and that they're perpendicular, so that the right angle formulation is a direct result by theorem of the lines being perpendicular, but the line segments that are formed by the intersection of the two diagonals are matched pair congruent line segments for the individual diagonals themselves, which is to say specifically that line segment DE and BE are congruent to each other. Notice they have two tick marks each. And then furthermore, line segment AE is congruent to CE rather. AE and CE are congruent line segments as well. So this gets to be a quite fun and interesting concept for you to play around with in the homework exercises. So if in the course of tackling those in your first effort you're just like a little bit confused here and there, obviously I just want to remind everybody that's a perfect opportunity to address this in class, and I'm happy to demonstrate any homework problems in 6.3 on the day in which that becomes the topic for the class period. Okay, now let's go ahead and tackle one example, and then we're gonna call it done on this last section of chapter 6. And then, of course, yes, like I just said, it's perfectly acceptable for you to ask me to demonstrate homework problems if this one example is not cutting it as far as assistance is concerned in completing your homework problem. So, but without further ado, let's go ahead and find the perimeter of the square shown. The square, of course, is inscribed inside of a circle, okay? Not that we know very much about circles in this class as far as the curriculum is concerned, but I do want to have you guys note that the dashed blue line right here appears to be the radius of the circle. Okay, so I am kind of assuming that you have some offhand knowledge of circles and radii. And what would happen if we continued this dashed blue line all the way to the other side? What length do you assume the center would have to this vertex of the square? Well, it would have to be the same length, wouldn't it? Because it would be another radius associated with the circle. And then also notice that as you continue this dashed blue line all the way across from one vertex to the non-adjacent vertex, that you're creating a diagonal for the square. And what is the collective distance of this diagonal? Well, half of it is 3 root 2's, the other half is another 3 root 2's. Add them all together and it's 6 root 2's, right? Okay, so we have the diagonal of the square having a length of 6 root 2. How does that help us get the perimeter of the square? Which, if you recall, the perimeter of a triangle was presented formally in class so far. I will just offhandedly define that the perimeter of any polygon is going to be the sum of the exterior edge lengths. And there's going to be 4 of them here for the square, and they're all going to be congruent, aka having the same measure. So, can we find the length of the outside edges using this diagonal? Yes, we can. If we recognize that the diagonal coupled with these 2 edges here that have the right angle as the measure of the vertex angle, holding those 2 edges together, form a right triangle. Do you guys see that? And so we can let the 2 legs of our right triangle be denoted by some unknown value. I'm going to go ahead and label it as x. And I'll let the other leg be labeled as x as well, because we know that all of the outside edges of our square are the same length. So this leg and this leg of the right triangle being considered are equal, and so we'll just call them the same unknown value of x. The hypotenuse of this right triangle is known to us, the length of it that is, as 6 root 2. So let's go ahead and use the, yes, you guessed it, Pythagorean theorem in order to create a relationship between those leg lengths. We'll square them and add them together and set that equal to the square of the hypotenuse, which also happens to be the diagonal of the square and also happens to be the diameter of the circle. It's all the same thing here. It's all very much beautifully connected. Okay, now let's put our algebra hat on and figure out what to do with solving this equation for x. So probably the first thing you'll want to do is combine like terms on the left-hand side. So you have 1x squared here, another x squared there. It looks like you have 2x squareds all together. So in the next step, I'll call this 2x squared on the left-hand side. On the right-hand side, notice that we have factors of 6 and root 2 being collectively squared. So we're going to have to use our power of a product rule, which more or less distributes that square exponent onto the 6 and onto the square root 2. Now when you square a square root, those are inverse operations of one another and they cancel each other out. So I should have 6 squared times root 2 squared on the right-hand side, as you can see. And then yes, on the left-hand side, as I mentioned before, I combined the like terms of x squareds. I have 2x squareds altogether. Great. Now, let's deal with this right here. The square root of 2 being squared, the square root, and the squaring, they will cancel each other out very much awesomely. And so I will get the square root of 2 being squared just settles down to the radicand, that's the technical term for the number inside of a radical of 2, and then we'll square the 6 as well, and that's how we'll get this 36 factor. Okay, at this point, you can either multiply the 2 and the 36 to get 72, or you can recognize that on both sides of your equation you have a factor of 2 that can be canceled out. That's what I would recommend that you focus on, is just divide both sides by 2, and then you will get x squared equals 36. Now, 36 happens to be a perfect square number, so if we square root both sides, we shall get x equals 6. Now notice, if you are being a strict algebraist with this problem, you might argue that, oh wait, hold on guys, x should equal plus or minus 6, but remember, x is representing the side length of a square. So it has to be a positive value. It's a distance. We don't deal with negative distances ever. Sometimes, you know, if we're talking about going below sea level, you could argue that that's represented by a negative number. Sure, sure, sure. But generally, distances, even if they don't have units, are represented by positive numbers. So when you are dealing with these kinds of problems where you're taking the square root of both sides, and your algebra brain will be like, oh God, I need to put two answers here, because technically there are two algebraic approved answers of plus or minus 6. Just take the principal square root, which is the positive one, because we're representing a distance. Okay, I think I over-explained that. Now, if x equals 6, then what will be the perimeter of this square? Because remember, we're not asking what x is. The original task was to find the perimeter of the square shown. So one of the edges has a length of 6, but there are 4 edges of length 6 altogether, so that means the perimeter is 24. There are no units, so don't worry about trying to force some kind of units or of centimeters or feet or anything like that. There are none, so go ahead and just label the perimeter as strictly the value in which you calculate, in this case the 24. Okay, that is all for today. Very short video to wrap things up, but please tackle as much as you can of this homework set, and then come to class ready to ask questions on any of the problems that you see here that you have further questions on. I'm happy to demonstrate them in class. You need only ask. And I look forward to seeing you for that class period very much soon. Okay? Take it easy. Take care of yourselves. I'll see you soon.